without a single bar turning into a mess. If the chocolate sets wrong or the caramel pulls too far, the whole texture falls apart instantly. In this video, we follow the lines from cocoa refining and aeration to wafer baking and wrapping, revealing the make or break checkpoints that keep every bite perfect. Cadbury dairy milk is manufactured by transforming milk and sugar and cocoa into a low moisture chocolate crumb or chocolate mass, refining it into a smooth suspension, conching it to stabilize flow, tempering it to lock stable cocoa butter crystals, then molding and packing while temperature and viscosity stay tightly controlled. Milk handling is treated as a structural step rather than a flavor step because dairy solids determine body and sweetness balance. Milk can enter as liquid milk, concentrated milk, or milk powder depending on plant design. Liquid streams are filtered and held at controlled temperature for predictable pumping. Powder streams are sieved to remove clods because clods do not hydrate evenly and later create texture specks. Sugar is screened to control crystal size and to remove lumps that would resist refining. Cocoa components are prepared as cocoa liquor and cocoa butter streams held warm so they remain pumpable. Cocoa powder streams are sifted when used to remove compaction lumps. All dry ingredients are kept low in moisture because water in chocolate causes thickening and unstable flow. A key feature of many milk chocolate lines in this style is crumb production, which converts milk and sugar into a dry solid that carries developed dairy notes and improves process stability. Crumb production starts by combining milk and sugar in a cooker. The mixture is heated while being mixed, so sugar dissolves and water begins to evaporate. Heating is controlled to drive off water without scorching milk solids. As water leaves, the mixture becomes thicker and begins to form granular solids. The cook continues until the mass becomes a dry or semi-dry crumb with low residual moisture. During crumb cooking, thermal history is tightly managed because it controls flavor development and functional behavior. Too gentle a cook leaves high moisture and produces crumb that later thickens the chocolate unpredictably. Too aggressive a cook darkens sugars and drives strong cooked notes that can overwhelm the profile. The endpoint is set by moisture content, and by the way, the crumb fractures when broken. When the endpoint is reached, the crumb is cooled and milled into a manageable size so it can be blended uniformly later. Cocoa liquor and cocoa butter are prepared in parallel. Cocoa liquor is held warm so it stays fluid and is filtered to remove solid lumps. Cocoa butter is melted in jacketed tanks and filtered for clean metering. These fat streams define the continuous phase of the final chocolate, and they also control viscosity through the downstream steps. Mixing combines crumb with cocoa liquor, cocoa butter, and additional sugar or milk solids as required by the recipe. The goal is to create a homogeneous pre-mass where solids are evenly distributed in fat. Mixing is done in high-torque mixers with wall scraping because the mass can be thick before refining. The mixture transitions into a paste with consistent color and no dry pockets. At this stage, the mass is not yet smooth. Sugar crystals and crumb particles are still large enough to be detected on the tongue. Refining is performed to reduce particle size. The pre-mass is fed to roll refiners or other milling systems. In roll refining, the mass passes through a series of rolls with decreasing gaps. Each pass squeezes and shears particles smaller. The refined output leaves the last roll as a thin film that breaks into flakes. These flakes have high surface area and must be processed into conching quickly to prevent moisture pickup. Conching is the step that transforms refined flakes into a smooth flowing chocolate with stable flavor. The flakes enter a conche where mechanical work coats each particle with fat and breaks down remaining agglomerates. Heat keeps cocoa butter fluid and supports moisture removal. Airflow through the conche carries away moisture and volatile compounds. Moisture removal is essential because even small amounts of water cause chocolate to seize and become thick. Conching also stabilizes rheology by reducing friction between particles. Early in conching, the mass can be dry and pasty. As fat distribution improves, the mass becomes smoother and viscosity drops. The concha profile is tuned to reach a target viscosity for molding and enrobing while maintaining the desired flavor. Over-conching can reduce throughput and strip some volatile character. Under-conching leaves high viscosity and inconsistent snap. Emulsifiers are typically added near the end of conching. Lecithin improves particle wetting and reduces yield stress. Another flow modifier can be used to reduce viscosity further at a given fat level. These additives are dosed precisely because small changes alter how chocolate behaves in deposit heads and tempering machines. The chocolate is then filtered and transferred to holding tanks with gentle agitation to keep the suspension uniform. Tempering is the controlled crystallization of cocoa butter that gives dairy milk its stable set and gloss. Chocolate is first heated to melt existing crystals fully. It is then cooled under agitation so new crystals form. It is then reheated slightly to melt unstable forms while keeping stable seed crystals. The output chocolate contains a controlled population of stable crystals and remains fluid at the working temperature. Temper is monitored continuously because it drives mold release and surface quality. If temper is too low, the chocolate sets slowly and releases poorly and can bloom later. If temper is too high, viscosity rises and the chocolate becomes thick, causing poor mold, fill and thick edges. Tempering machines adjust cooling and heating in small increments to maintain the target crystal content. Molding shapes the chocolate into bars and blocks. Polycarbonate molds are cleaned and pre-warmed to prevent condensation. Depositors meter chocolate into each cavity with tight mass control. The filled molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also improves detail in any embossed features. Cooling tunnels set the molded chocolate. Cooling is staged to set the surface quickly without creating internal stress. The chocolate contracts slightly as it cools, which helps demolding. If cooling is too fast, the chocolate can crack or warp. If too slow, the line speed drops and molds remain occupied. Cooling also must avoid condensation because moisture on the surface can cause sugar bloom. After cooling, the molds are inverted and the bars release. Release depends on correct temper and correct cooling because the bar must contract away from the mold wall. Bars transfer to conveyors where they are inspected for surface defects. Weight checks confirm deposit accuracy. Bars with defects are diverted for rework. Rework is remelted and returned upstream in controlled ratios so it does not destabilize tempering. If the product includes inclusions or filled formats, the molding stage expands. Inclusions, such as nuts, are screened and kept dry. They can be placed into molds before chocolate deposition or blended into chocolate with controlled suspension. Filled formats use sequential depositing. A shell is deposited and partially set. A filling is dosed and then sealed with a chocolate back layer. Cooling profiles are adjusted because fillings change heat transfer and can insulate. After demolding, bars move to wrapping. Wrapping protects chocolate from oxygen, moisture, and abrasion. Bars are indexed into wrapping machines that fold foil or film around each bar. Fold geometry is controlled so edges are crisp and seals are tight. If an inner foil and outer paper wrap are used, the foil provides the barrier and the paper provides stiffness and print. Heat sealing or crimping forms the closure, depending on wrap type. Coded information is applied during wrapping or immediately after. Vision systems check wrapper alignment and seal integrity. Check weighers verify pack weight. Wrapped bars are then collated into cartons if needed. Cartons are erected and filled with a defined count. Cartons are closed and glued. Finished units are case packed and palletized. The process control backbone for dairy milk is moisture management and particle size management and crystal state management. Crumb production drives moisture down and creates a stable dairy sugar matrix. Refining drives particle size down for smoothness. Conching drives off remaining moisture and stabilizes flow by coating particles with fat. Tempering builds the correct crystal population for gloss and snap and clean mold release. Cooling locks the structure and wrapping protects it from temperature swings and humidity. Three Musketeers is manufactured by producing a highly aerated chocolate-flavored nougat center, forming it into a continuous slab, cutting it into bars, enrobing those bars in tempered chocolate, then cooling and wrapping while density and coating thickness remain tightly controlled. The defining step is the aeration system, because the bar's texture depends on holding a large volume of fine bubbles inside a stable sugar and fat matrix. The process, therefore, starts by building two streams that can be combined without collapsing air cells. One stream is a cooked syrup with a precise solids level. The other stream is a foamed phase that carries air at a controlled density. Syrup preparation begins with sugar and glucose syrup metering. Granulated sugar is screened to remove clumps and to keep dissolution predictable. Glucose syrup is held in jacketed tanks so it pumps at stable viscosity. Water is filtered and tempered because inlet temperature affects dissolving rate and cooker stability. The streams enter a dissolver where agitation produces a clear solution. Strainers remove any undissolved grains because grains concede crystallization and create a gritty center. The clear syrup then enters a continuous cooker where heat drives off water. Many systems heat under pressure, so temperature can rise quickly without boiling in the coil. After the heating zone, the syrup may enter a flash stage where pressure drops and water vapor leaves rapidly. This trims moisture to the target. Moisture control here sets final nougat resilience. Too much moisture yields a soft center that can deform under cutters. Too little moisture yields a tough center that loses its light bite. While the syrup is being cooked, the aerated phase is prepared. A protein solution is mixed to a defined concentration and then sent to a continuous aerator. Airflow and rotor speed are controlled to create small bubbles and stable foam. Foam density is monitored continuously because it is the most direct indicator of final bar lightness. The foam must be stable enough to survive contact with hot syrup. It must also be fine enough to produce a smooth bite rather than large voids. The cooked syrup is cooled slightly to a controlled blending temperature and then combined with the foam in a continuous mixer. The mixer is designed to fold the streams together rather than whip. Folding distributes syrup through the foam while preserving the bubble structure. The syrup heat partially sets the protein films around bubbles and locks in the microcell network. Chocolate flavor is built into the nougat by adding cocoa components and sometimes chocolate liquor or cocoa powders at controlled points. These additions must be dispersed without deflating the foam. They can be introduced as fine powders, pre-blended with part of the syrup, or as a liquid chocolate. Stream introduced downstream of the highest shear zone. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be added in small doses to improve stability and control viscosity. Once mixed, the aerated nougat exits as a warm plastic mass with controlled density and viscosity. It is deposited onto a moving belt as a continuous slab. A spreader head lays down the slab at a defined width. Gauge rollers and leveling bars set thickness. Thickness control is critical because it determines bar mass and also affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Staged cooling prevents a hard skin from forming over a warm interior because that skin can crack and create weak planes during cutting. As the slab cools, the bubble structure stabilizes further. Fat begins to crystallize, and the nougat transitions from plastic to firm yet compressible. The target firmness is set so the slab can be cut cleanly without smearing. If the slab is too warm, knives drag and deform edges. If too cold, the slab can fracture at the surface and create rough edges that show through the chocolate coat. Edge trimming is often used to remove uneven slab edges. Trims are collected as controlled rework. Rework must be managed carefully because aerated material behaves differently than fresh mix. Excess rework can shift density and bubble size distribution. The main slab then moves into lane cutting. Rotary knives slice the slab into long ropes of constant width. A crosscutter then slices the ropes into bar lengths. Cutter timing is synchronized with belt speed, so each bar length is consistent. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between bars. Transfer points are designed with low drops and soft transitions because aerated centers dent easily. Some lines include a brief pre-chill to firm the surface. Firmer surfaces accept chocolate more evenly and reduce deformation as the center passes through the curtain. Chocolate coating is prepared in a separate system where temper is the key variable. Chocolate is melted and filtered to remove unmelted particles. Tempering then creates stable seed crystals by controlled cooling and reheating. Working temperature is set so viscosity remains stable at the curtain. Viscosity controls the thickness of the coating and therefore the final chocolate to center ratio. Enrobing coats the bar with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a roller or a bath section that lays a consistent base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot at the base. Air knife settings are tuned to remove excess without exposing corners. Because the center is soft, air knife force is balanced so it does not deform the nougat under the coat. A pattern top can be applied by a stringer that drizzles thin chocolate lines over the wet surface. The drizzle must bond before the base coat fully sets. This requires a precise timing window between curtain exit and cooling tunnel entry. Pattern flow rate and nozzle spacing are synchronized with belt speed. Cooling tunnels set the chocolate. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling must avoid condensation because moisture on chocolate creates sugar bloom and dullness. Tunnel humidity is controlled, and the bar exit temperature is set to support wrapping without scuffing. During cooling, the nougat center also equilibrates. The fat phase in the center continues crystallizing, and the bubble walls become more rigid. The center remains light and compressible, but it gains enough strength that handling pressure from wrappers does not deform it. The chocolate coat becomes a barrier that reduces moisture exchange and helps maintain texture over shelf life. Inspection follows cooling. Vision systems check for exposed edges and coating voids. Weight checks confirm bar mass and coating mass. Bars outside tolerance are diverted. Diverted product is handled as rework streams that are remelted for chocolate or reprocessed for nougat according to process rules. Wrapping begins once the bars reach a stable temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are controlled, so seals are tight without shrinking film onto the bar. Film tension is controlled to avoid scuffing the chocolate surface. Print registration aligns graphics to bar position. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Twix bars are manufactured by producing a crisp biscuit finger, applying a controlled caramel layer, enrobing the assembled sticks in tempered chocolate, then cooling and wrapping while moisture and viscosity remain tightly controlled. The process begins with the biscuit line because the biscuit defines the bar geometry and the snap that must survive caramel deposition and chocolate coating. Flour is sieved to remove lumps and to standardize flow. Sugar is screened so crystal size is consistent and does not tear dough during mixing. Fat is conditioned to a plastic state so it blends evenly and limits gluten development. Leavening salts are weighed precisely because they determine porosity and bite strength. Water and any dairy liquids are tempered because dough temperature controls how cleanly it sheets and cuts. Mixing is designed to create a short dough with limited gluten. Fat and sugar are first blended to distribute fat and reduce dry friction. If a creaming step is used, it is controlled to avoid excessive air because too much air weakens biscuit and increases breakage during handling. Dry ingredients are then introduced and mixed only until the dough becomes cohesive. Minimal mixing limits gluten formation and preserves a tender, crisp structure rather than a tough one. Dough conditioning follows. The dough rests so moisture equilibrates and the dough relaxes. Relaxation prevents snapback during sheeting. Dough temperature is held in a narrow range, so fat stays plastic. Warm dough smears on rollers. Cold dough cracks at edges and produces rough cutouts. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through reduction rollers that gradually thin it. Gauge rollers set final thickness tightly because thickness drives bake time and final snap. Dusting flour can be applied sparingly to prevent sticking, but excess dust is avoided because it burns and creates specks. The sheet enters rotary cutting and docking. Rotary cutters punch long biscuit fingers. Docking pins create small holes through the dough. These holes vent steam during baking and prevent blistering and warping. The cut fingers transfer to an oven band. Scrap dough around the cutouts is lifted and recycled. Scrap ratio is controlled because repeated working increases gluten and changes dough behavior. Baking occurs in a tunnel oven with staged zones. Early zones set the shape as fat melts and moisture begins to leave. Leavening gases expand and create small pores. Mid-zones drive moisture down and develop a light golden color. Later zones finish drying so the biscuit reaches a low moisture endpoint. Moisture endpoint is critical because the biscuit must remain crisp under caramel and chocolate. If moisture remains too high, the biscuit will soften and lose snap. If moisture is too low, the biscuit becomes overly brittle and breaks during sandwiching and wrapping. After baking, the biscuit fingers exit the oven and enter cooling. Cooling stabilizes structure as fats re-solidify. Cooling air is controlled and often dehumidified because dry biscuits can absorb moisture from humid air. The goal is a consistent exit temperature and moisture level. The cooled fingers are then aligned into lanes for caramel application. Caramel production runs in parallel because caramel must be depositable and stable. Sugar and glucose syrup are cooked with milk components to develop caramel flavor and reach an elastic solids endpoint. The cook drives off water until the caramel will hold shape at room temperature. Fat is added to smooth the caramel and reduce tack. The endpoint is set so the caramel bites cleanly without becoming glassy. Overcooked caramel becomes hard and can fracture when the bar is bitten. Undercooked caramel flows and smears in packaging. Caramel is cooled from cook temperature to a working temperature where viscosity is stable for deposition. It is held in jacketed tanks with gentle agitation to prevent skin formation. Pipes to the depositor are heated to prevent cold plugs. Viscosity is monitored indirectly by pressure and flow because a small temperature drift changes deposit weight and layer thickness. caramel deposition applies a continuous layer onto the biscuit fingers. A slot depositor or multi-nozzle head lays caramel onto the moving biscuit lane. A leveling bar smooths the surface and sets thickness. Thickness must be uniform because it influences bite and chocolate coverage. If caramel is too thick, it can squeeze out under chocolate and create uneven edges. If too thin, the bar loses the intended caramel to biscuit balance. The biscuit temperature at deposition is controlled. Biscuit must be cool enough to remain crisp and to avoid melting caramel into the pores too deeply. It must not be so cold that caramel fails to bond. The line targets a temperature window where caramel adheres but does not soak. After deposition, the caramel-topped fingers pass through a cooling tunnel to set the caramel surface. Cooling must be staged so the surface firms without cracking. A firm surface is required before enrobing so caramel does not smear on belts. Once the caramel is set, the sticks are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfers minimize drop height because biscuit can crack and caramel can shear. The sticks may pass through a brief pre-chill to firm surfaces and improve chocolate flow behavior. Chocolate preparation is a separate stream where temper control is essential. Chocolate is melted and filtered. It is tempered to create stable cocoa butter seed crystals. Working temperature is set to maintain consistent viscosity. Viscosity determines how thick the chocolate curtain is and how much chocolate remains after air knife trimming. Enrobing coats the sticks in chocolate. A top curtain covers the caramel and sides. A bottoming system coats the underside so the biscuit is sealed. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot thickness. Air knife settings must be tuned because too much air can expose corners, especially at biscuit edges. Too little air leaves thick feet that can crack during cooling. If a top pattern is required, it is applied immediately after the main curtain. A stringer deposits thin chocolate lines across the surface, while the base coat is still wet enough to bond. The stick then enters the cooling tunnel. Cooling sets the chocolate and locks the finished structure. The first zone sets the surface quickly to prevent slumping. Later zones cool gradually to promote stable crystal growth and reduce bloom risk. Cooling also reduces the internal temperature of caramel so it reaches its final elasticity. The exit temperature is set so the chocolate is hard enough for wrapping without scuffing. After cooling, the bars are inspected. Vision systems detect exposed biscuit corners and coating voids. Weight checks confirm portion control. Defective bars are rejected. Rework chocolate is remelted and returned upstream, while biscuit and caramel rework is handled separately because it carries moisture and texture changes. Wrapping begins with feeding bars into flow wrappers. Film is formed around each bar and sealed. Seal temperature and dwell are controlled so seals are strong without overheating the chocolate. Film tension is controlled to prevent scuffing. Print registration aligns graphics. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station, where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the cream filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt, where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. Agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill confirmation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch-wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella B-Ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella B-Ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Celsius within 2 minutes. Simultaneously, Nutella filling is prepared in a separate processing room using a continuous mixing system. Ingredients including refined sugar, vegetable oil, skimmed milk powder, cocoa, and hazelnut paste are dosed using mass flow meters and pneumatic transfer lines. Mixing occurs in a double-jacketed emulsification vessel with counter-rotating impellers operating at 800 to 1200 RPM. The temperature is held between 40 degrees and 45 degrees C during mixing to maintain fluidity and preserve emulsion stability. The finished Nutella filling is pumped through heat-insulated stainless steel piping into buffer tanks connected to multi-head depositor units. These depositors are aligned with the conveyor lanes carrying the pre-formed wafer shells. Each depositor nozzle dispenses a precise amount of filling, usually between 12 and 16 grams, into the hollow cavity of each wafer. Fill weight is monitored using inline load sensors that reject any units outside the tolerance band of plus 0.3 grams. To prevent air entrapment during deposition, the filling nozzle retracts during injection at a synchronized rate, matching the filling viscosity and back pressure. Cream flow is assisted by low-pressure nitrogen to maintain a consistent stream and eliminate pulsing. After filling, each shell passes through a cooling tunnel maintained at 10 to 12 degrees to solidify the fat phase of the filling and prevent oil migration into the wafer wall. Following cooling, a pre-molded wafer lid is applied to seal each filled shell. These lids are formed from the same dough and are baked separately on a synchronized rotary system. A robotic arm equipped with vacuum suction cups picks and places each lid onto the open cavity. An edible adhesive compound, typically a glucose-based syrup, is applied to the perimeter edge to create a bond. Pressure rollers compress the lid and base together for mechanical adhesion. After sealing, each unit passes through a mechanical inspection station. High-speed cameras and laser profilometers verify shell integrity, alignment, lid placement, and overall dimensions. Any product with cracks, offset seals, or excessive height deviation is automatically rejected via pneumatic diverter arms. Approved units move into the packaging preparation line. Packaging begins with flow wrapping. Individual Nutella B-Ready units are spaced on timing belts and fed into the wrapping machine using servo motor controlled pushers. Wrapping film is fed from a roll and formed around each unit via a forming collar. Horizontal and vertical seals are applied using heated sealing jaws that operate at 130 degrees, 145 degrees. Modified atmosphere packaging is implemented via nitrogen gas injection prior to sealing to displace oxygen and extend shelf life. Each flow-wrapped unit is scanned by barcode readers and printed with date codes and traceability numbers using thermal inkjet printers. Units are counted and grouped into sets of 6 or more, depending on market configuration. Grouping is performed using star wheel collators, which align the units into rows for secondary packaging. Secondary packaging uses flat fold cartons erected via vacuum cup pick-and-place systems. hot melt glue is applied via nozzles to predefined folding flaps, which are pressed closed by mechanical arms. Each carton receives printed labels containing product name, nutritional data, batch code, allergen information, and certification marks. Cartons are weighed for content verification and stacked into larger corrugated shipping boxes using layer-forming robotic packers. Palletizing is performed by 6-axis robotic arms with end effectors designed to grip multiple boxes per cycle. Standard Euro or industrial pallets are loaded based on customer logistics requirements. Pallet patterns are configured to ensure structural stability and airflow clearance. Once loaded, pallets are wrapped using stretch film machines that apply 250% pre-stretched film to secure load integrity during transit. Each pallet is tagged with a pallet license plate containing full production metadata, including line number, production date, shift code, storage conditions, and destination route. Pallets are moved into finished goods, storage warehouses with temperature and humidity control systems set to maintain between 18 degrees Celsius and 20 degrees, with relative humidity under 60%. Pallet positions are recorded using warehouse management systems with RFID scanners and barcode tracking. Throughout the production process, all inputs, outputs, and in-process conditions are monitored by a centralized SCADA system. Parameters such as oven temperature, mixer torque, depositor cycle counts, wrapping seal integrity, and product rejection rates are logged and archived. Alerts are generated automatically for any deviation outside programmed thresholds. Operators access these systems via HMI touchscreens placed at each station. Sanitation protocols are applied on a rotating schedule. Dough preparation lines are cleaned with dry brushing, followed by ethanol-based surface wipes. Cream handling equipment undergoes full CIP cycles involving alkaline wash, acid rinse, and sterile water flush, validated with conductivity and pH sensors. Wrapping and cartoning stations are cleaned with compressed air, brush downs, and isopropyl surface sanitizers. Swab samples are taken post-cleaning and tested for microbial load. Preventive maintenance is performed weekly on all forming dies, depositor heads, conveyor bearings, and sealing modules. Wear components are replaced based on run-hour tracking. Calibration is conducted daily on dosing equipment, weighing scales, and thermocouples. All calibration records are maintained in compliance with regulatory documentation standards. Product testing occurs hourly. Samples are collected from each production lane and evaluated for weight, length, height, filling content, shell texture, seal strength, and packaging tightness. Sensory analysis includes bite resistance, shell-to-filling ratio, and flavor consistency. Non-conforming samples trigger root cause investigations documented in deviation reports. The entire Nutella B-Ready manufacturing process is standardized to allow for duplication across multiple production facilities with identical output quality. Parameters are optimized to prevent moisture migration, mechanical breakage, and oil separation, which are common defects in filled wafer-based snack formats. Final product shelf life is tested under accelerated and ambient conditions to verify packaging efficacy. Chips Ahoy. Cookie manufacturing begins with bulk ingredient handling systems that store raw materials in separate silos or intermediate bins under controlled conditions. Low moisture, fine milled wheat flour is pneumatically conveyed from outdoor silos into batch weigh hoppers located above the main mixing area. Granulated sugar, brown sugar, cocoa solids, salt, and baking soda are stored in indoor silos or gravity-fed bins and fed into weigh stations using screw feeders with plus 0.1% dosing precision. Vegetable shortening and liquid invert sugar are stored in stainless steel jacketed tanks with continuous recirculation to prevent phase separation. The shortening is heated to maintain fluidity at 45 to 50 degrees Celsius, and the invert sugar is pumped at a constant rate through positive displacement pumps. All liquid and dry ingredients are tracked using an integrated batching control system that verifies real-time mass flow and batch integrity using load cells and flow meters. Each batch is loaded into a planetary batch mixer with a dual paddle agitator system. Mixing follows a 3-stage time-controlled sequence. First, creaming of shortening and sugars is performed for 3 to 4 minutes at low speed. Next, flour and leavening agents are incorporated at medium speed for an additional 3 minutes. Finally, the mixture is scraped down and mixed on high speed for 1 to 2 minutes until a homogeneous dough with uniform texture and target moisture content of 18 to 20% is achieved. Temperature sensors monitor the dough throughout mixing to ensure it remains within the 20 to 24 degrees Celsius range. Overheating is prevented by jacketed cooling systems circulating chilled glycol solution. Once the dough is fully mixed, it is discharged into a stainless steel hopper that feeds a cookie depositor via auger conveyors. Before entering the depositor, chocolate chips are metered into the dough using volumetric feeders to achieve a distribution ratio of approximately 20% by weight. The cookie depositor uses servo-controlled pistons to extrude uniform dough portions directly onto a continuously moving Teflon-coated oven band. Deposit weight per cookie is calibrated to between 18 and 21 grams, depending on SKU. Deposited dough pieces are spaced using optical sensors to maintain consistent center-to-center distance and allow for uniform spread during baking. Each dough piece is flattened slightly by a roller to control shape retention. The baking oven is a hybrid convection and radiant tunnel oven with multiple independently controlled heating zones. Total bake time is typically between 8 and 11 minutes. The oven band runs at a set speed that is continuously adjusted by a PID controller based on real-time surface temperature and humidity readings. Oven zone temperatures range from 160 degrees Celsius in early zones to up to 210 degrees Celsius in final zones to ensure progressive starch gelatinization, moisture evaporation, Maillard reaction, and fat migration. Cookies are monitored during baking using infrared pyrometers that measure surface temperature. Steam injection systems in early oven zones are optionally used to control surface moisture and prevent excessive cracking. Exhaust fans in later zones remove excess humidity and volatile compounds. By the time cookies exit the oven, internal moisture content is reduced to between 3 and 5%, ensuring shelf-stable texture and microbial safety. Upon exiting the oven, cookies are transferred onto a wire mesh cooling conveyor system. Ambient air is directed from below and above the belt using axial fans to achieve uniform cooling to under 30 degrees Celsius in less than 3 minutes. Sensors at the end of the cooling belt check surface temperature before transferring cookies to the inspection area. Conveyor vibrations are minimized to prevent cookie breakage during transfer. Each cookie passes under a vision inspection system equipped with high-resolution cameras and infrared lighting. Software algorithms evaluate cookie shape, surface cracking, chip dispersion, color uniformity, and diameter tolerance. Any cookies failing to meet visual standards are rejected using high-speed air jets. All rejected cookies are weighed, logged, and diverted to waste bins for offline handling. Approved cookies move to the packaging station via a system of vibratory conveyors that align and group the cookies into required configurations. For multi-pack packaging, cookies are grouped into stacks using rotary collators and staged for wrapping. Individual flow packs are created using horizontal form-fill-seal machines. Film is pulled from rolls, shaped around each cookie group, and sealed using heated crimp jaws operating at 130 to 150 degrees Celsius. Modified atmosphere packaging may be used with nitrogen flushing to reduce oxygen and delay lipid oxidation. Each wrapped package receives a printed date code, batch code, and line identification number using thermal inkjet printers synchronized with the conveyor belt. Packages are weighed on inline check weighers with rejection arms for any unit falling outside of mass tolerances. Wrapped units are inserted into cartons using robotic pick-and-place arms with vacuum grippers. Cartons are sealed with hot melt glue at 165 degrees C and pressed under controlled pressure to ensure full adhesion. Secondary packaging lines aggregate cartons into shipping cases. Cases are erected from flat blanks, filled automatically, and closed with either glue or tape depending on distribution requirements. Completed cases are printed with pallet codes, production timestamps, and destination routing labels. Automated guided vehicles, AGVs, or roller conveyors transfer cases to palletizers. Palletizing robots layer the cases using defined stacking patterns optimized for pallet stability and load efficiency. Each pallet is scanned for completeness using weight and barcode validation before being stretch wrapped in polyethylene film at 250% pre-stretch. Wrapped pallets are moved to finished goods warehouses with controlled temperature and humidity, typically 18 to 20 C and 50 to 60% RH. Every stage of the process is controlled and logged using a manufacturing execution system, MES. Batch records include ingredient lot numbers, mixing parameters, bake curves, oven temperatures, deposition weights, packaging counts, inspection rejections, and finished product quantities. Quality control technicians collect hourly samples to perform destructive and non-destructive testing on cookies. Tests include diameter measurement with calipers, moisture analysis via moisture, analyzer, texture profile analysis using 3-point bending rigs, and chip count per cookie via manual visual audit. Organoleptic tests include bite resistance, sweetness intensity, and flavor profiling under controlled conditions. Data is stored electronically and checked against specification ranges defined in the product specification documents. Production lines are cleaned on a rotating schedule. Between batches, dry cleaning is performed using brushes and vacuum systems to remove flour dust and crumbs. At daily intervals, equipment is disassembled and sanitized using foaming alkaline cleaners, followed by water rinses and food-safe sanitizers. Chocolate lines undergo specialized cleaning to prevent fat bloom and cross-contamination. Allergen control zones are enforced through physical separation of lines, color-coded tools, and allergen-specific cleaning validations. Swab tests for protein residues are performed on high-contact surfaces after each cleaning cycle. If any allergen residue exceeds the defined limit, cleaning is repeated and verified before production resumes. Downtime events such as depositor jams, film feed interruptions, or oven temperature deviations are tracked via the line control system. Operators record the event time, cause, and corrective actions. Line productivity is measured using overall equipment effectiveness (OEE) metrics, including availability, performance, and quality yield. Preventive maintenance on mixers, ovens, conveyors, depositors, and packaging machines is scheduled based on runtime hours. Critical components such as servo motors, bearings, seal jaws, and roller chains are monitored for vibration and thermal performance. Spare parts inventory is maintained in real time using a computerized maintenance management system, CMMS. Finished product samples are retained from each batch for shelf life testing. These samples are stored under accelerated and ambient conditions and tested at intervals for texture degradation, moisture migration, lipid oxidation, and packaging integrity. Results are used to confirm product expiration dates and to evaluate packaging material performance. All operations conform to global food safety standards such as GFSI benchmarking and are subject to internal audits and third-party certification. Traceability systems allow for immediate upstream and downstream tracking of all product components within minutes of any query. Any deviations from process controls trigger root cause analysis under a corrective and preventive action (CAPA) protocol. Dunkin' Donuts production starts with formulation of base dough using a high-capacity spiral mixer. Ingredients are loaded automatically through overhead dispensers connected to silos and tanks. The dry phase includes high-gluten wheat flour, sugar, salt, non-fat dry milk, and dough conditioners. Liquid components include water, whole eggs, vegetable shortening, and yeast. Ingredients enter the mixing chamber in a fixed order to ensure consistency. Flour is dispensed first into the bowl, followed by sugar and salt through calibrated rotary valves. Shortening is pre-melted in a jacketed vessel and dosed into the bowl using a metered pump. Liquid eggs are held in chilled tanks and dispensed through a pneumatic valve. Yeast is hydrated in a separate tank before being introduced into the mix stream. Mixing begins at a low speed to hydrate the flour and form gluten strands. The mixer transitions to a higher speed to fully develop elasticity. Total mixing time ranges between 8 and 12 minutes depending on batch size and target temperature. Bowl temperature is monitored through probes to prevent overheating. Once dough reaches optimal extensibility and temperature, it is discharged into a dough handling conveyor. This conveyor feeds a volumetric divider equipped with servo-driven pistons that portion dough into uniform units. Each portion is shaped into a ball using a rotary rounder. Rounded dough balls are transported by a belt conveyor into a multi-level proofer cabinet. Inside the cabinet, humidity and temperature are controlled to activate yeast fermentation. The dough rests for 30 to 60 minutes based on size and environmental conditions. After proofing, dough pieces exit the cabinet and enter a forming machine configured for ring shapes. A sheeter flattens each piece to a fixed thickness. A dual-blade rotary cutter stamps the dough into rings and removes the center to create the hole. Waste dough is automatically conveyed back to the hopper for reprocessing. Cut dough shapes are placed onto paper-lined proofing trays by a pick-and-place arm. Trays are loaded onto racks that feed into a secondary proofer tunnel. This tunnel maintains consistent humidity and temperature for final rise. Final proofing continues until dough height reaches preset targets. Proofed rings are then transferred onto a mesh belt conveyor leading into the frying system. The fryer is filled with vegetable oil, maintained at 190 degrees Celsius using immersion heating elements. The belt submerges each donut halfway and flips it midway to ensure even browning. Frying time is approximately 90 seconds per side. Excess oil is removed at the fryer exit using an inclined drip section. A vibrating shaker assists in shedding residual surface oil. Donuts proceed to a cooling conveyor that circulates ambient air over the surface to reduce internal temperature before finishing. Cooled donuts are sorted into finishing lines based on type. Plain rings move to the glazing station, which includes a curtain coater that pours warm sugar glaze over moving donuts. Excess glaze is recovered by a recirculation pump. Coated donuts pass under an air knife to remove drips and ensure uniform coating. For powdered sugar varieties, donuts are diverted into a tumbling drum. Fine sugar is dispensed into the drum continuously as donuts rotate inside. The tumbling motion creates full surface coverage. Sugar fines are filtered and reused through a vibratory sifter. Chocolate-coated donuts are transferred to an enrobing line. Melted chocolate compound is maintained at 38 degrees Celsius in a reservoir and pumped to a waterfall applicator. Donuts pass under the waterfall and receive a full coating. An inline cooling tunnel solidifies the chocolate layer. Filled donuts follow a different path. These start as solid discs cut from sheeted dough and proofed separately. After frying and cooling, each unit is aligned on a conveyor with a multi-nozzle injection machine. The filling system uses positive displacement pumps to inject jelly, custard, or cream into each donut at a fixed volume. Nozzles penetrate the side and retract automatically after filling. Decorated donuts are moved to a robotic icing station. Each robot arm uses a temperature-controlled piping nozzle to apply icing patterns or toppings. Sprinkles are deposited via gravity-fed hoppers positioned above a vibrating grid. Icing is cooled rapidly with a chilled air tunnel to prevent smearing. Donuts requiring packaging are grouped using a photo eye sensor and placed into trays by a robotic loader. Trays are conveyed to the overwrapping station where a film is wrapped and sealed using a heated jaw. Packaged trays proceed to a labeling machine that applies product and date information. Donuts intended for retail stores are stacked into crates by a pusher arm. Crates are conveyed to a loading dock and stored in temperature-controlled bays before transport. Crate movement is sequenced based on product age to maintain first-in, first-out flow. Throughput is maintained by synchronizing mixing, proofing, frying, glazing, filling, and packing stages. Any discrepancy between steps is corrected by buffer zones built into the conveyor system. Sensors at each handoff point check for weight, position, and spacing. Dough properties are controlled through water temperature, flour hydration, and mixer speed. Yeast activity is adjusted using proofing time and sugar content. Fry color and texture are determined by oil temperature, dwell time, and surface evaporation rate. Glaze thickness is adjusted by flow rate and curtain gap. Chocolate viscosity is controlled with continuous mixing and temperature monitoring. Filling density depends on nozzle diameter and injection pressure. Sprinkle adhesion is determined by icing tack time and coating temperature. Rework dough is monitored to prevent excessive cycles which could affect gluten structure. Oil is filtered continuously through a mesh screen and replenished to maintain performance. Icing and glaze are discarded after exceeding hold time limits. Mechanical components are cleaned using a clean-in-place system for mixers and pumps. Fryer oil is drained and replaced after a fixed number of cycles. Filling stations are purged between flavor changes using heated rinse cycles. Donut size is kept uniform through automated cutting, proofing, and handling. Each unit is weighed inline using load cells before frying. Out-of-spec pieces are rejected by air jets and sent to waste bins. Color is monitored by optical sensors after frying and coating. Each production run is tagged with a digital identifier that tracks every batch of dough from mix to packaging. Operators interface with the line through touchscreen HM is that adjust process parameters and initiate recipe changes. The ring shape is maintained by cutter pressure, proofing time, and dough elasticity. Hollow centers expand predictably when gluten structure and gas production are balanced. Sidewalls form evenly when frying is performed at the correct temperature gradient. Filled donuts expand less during frying due to the absence of a central void. Filling volume is calibrated to prevent leakage and to ensure weight compliance. Injection heads are sanitized between runs using a self-cleaning piston flush system. Production of limited-time donuts uses custom molds or dies fitted to the standard sheeting line. These are swapped in and out using quick-release clamps mounted on the cutting head. All process conditions remain unchanged except for shape and possibly finish. The Dunkin' Donuts production process is defined by sequential control over dough preparation, shaping, frying, finishing, and packaging. No stage is manually operated after initial ingredient loading. All transfers are automated and time synchronized. Mechanical reliability is ensured through routine calibration of volumetric dividers, fryer controls, coating pumps, and injection systems. Sensors detect clogging, misalignment, or loss of temperature and alert the PLC for correction. Air quality around finishing zones is maintained using filtered ventilation that prevents icing contamination. Powder applicators are enclosed and use vacuum returns to contain sugar dust. Chocolate lines are enclosed and climate controlled to prevent blooming. Every donut passes through at least 8 separate mechanical systems before final packaging. Each system modifies dough, temperature, texture, filling, or coating in a defined and repeatable way. The outcome is a donut with precise dimensions, weight, color, and taste profile. Wendy's burgers begin with raw ground beef held in refrigerated stainless steel bins, fitted with auger-driven dispensers. The beef is pre-ground to a fixed particle size and loaded into a hopper positioned above the patty forming system. The patty forming machine uses a hydraulic ram to compress a measured quantity of beef into a square mold. The square mold consists of a cavity with sharp edges and adjustable depth to control thickness. The beef enters the mold vertically and is pressed to a target shape using downward force. A release plate ejects the formed patty onto a conveyor belt lined with a non-stick food-grade belt material. The patties travel on the belt to a pre-cooked staging zone where they are spaced using an optical sensor and gating arm. Each patty is indexed into a clamshell-style contact grill, which applies uniform pressure from above and below. The upper platen is heated with embedded electrical elements and lowered using pneumatic pistons. The bottom platen remains fixed and maintains a set temperature through thermal sensors. Cook time is controlled by belt speed and platen temperature. Average dwell time for each patty is between 100 and 120 seconds, depending on thickness and grill load. Internal patty temperature is monitored using inline thermal probes, which retract automatically after contact. Surface browning is caused by Maillard reactions accelerated by the grill temperature. Rendered fat drains through grooves in the lower platen and is collected in a drip pan. Excess steam is evacuated through a hood system positioned directly above the grill zone. Once cooked, the patty exits the grill and moves onto a staging tray held at a constant holding temperature using a heat lamp array. While patties are cooking, buns are prepared on a separate toasting line. Buns arrive from storage in trays and are unloaded onto a conveyor. The bun separation system uses rotating paddles to split top and bottom halves and align them face down on the line. Each bun half passes under a radiant toaster element, which operates at a fixed distance above the surface. Toasting time is determined by conveyor speed and element intensity. Bottom buns are toasted slightly longer than top buns to handle moisture from toppings. After toasting, buns proceed to the assembly belt where they meet other components. Burger toppings are prepared on parallel preparation lines. Leaf lettuce is pre-cut and washed, then stored in chilled bins and dispensed manually into bins along the line. Tomatoes are sliced using a rotary blade slicer that maintains uniform thickness. Slices are collected into trays and moved to the topping line by belt conveyor. Onions are peeled and cut using an automated ring slicer and loaded into shallow pans. Pickles are pre-sliced and held in brine-filled containers until use. Cheese slices are separated by a vacuum picker and fanned out onto a chilled tray. Condiments, including mayonnaise, ketchup, and mustard, are dispensed using trigger-activated pumps that release a fixed volume per stroke. Dispensers are calibrated to deposit evenly without spread beyond the bun area. Burger assembly begins with bottom buns moving along a belt aligned with the topping line. A pump dispenses mayonnaise directly onto the bun in a circular pattern. A square cooked patty is placed onto the bun using a precision-guided placing arm, or manually depending on station configuration. Cheese slices are placed directly on top of the hot patty, which softens the cheese slightly but does not fully melt it. Sliced tomato is added next by tongs or fingers placed at center alignment. A leaf of lettuce is layered over the tomato and adjusted to not overhang the bun. Onion rings are laid flat across the lettuce with no stacking. 2 or 3 pickle slices are placed side by side depending on diameter. Ketchup and mustard are dispensed in zigzag or dot patterns based on the specific burger recipe. The top bun is retrieved from its place on the parallel conveyor and inverted onto the built stack using a rotating arm. The complete burger is then moved forward to a wrapping station where it is enveloped in printed foil or wax paper. Wrapping is done by folding each side toward the center and then folding the base upward before rolling the package forward. Wrapped burgers are placed into holding bins arranged by product type. Bin trays are heated from beneath with radiant elements to hold temperature. Burger names and identifiers are shown on digital displays above each bin. The wrapped burgers are then pulled in the order of assembly requests from service or drive-through lines. For specialty burgers with additional ingredients, separate modules are added to the line. Bacon is pre-cooked in convection ovens and held on heated trays. Spicy toppings or sauces are dispensed through separate triggers. Extra patties are added by adjusting tray positions to align multiple cooked patties before final topping. The entire burger line is modular and designed for high throughput. Each step, from toasting to wrapping, is timed and paced using conveyor intervals and operator rhythm. Cooked patties are used within a fixed window to maintain thermal properties during assembly. The square patty shape aligns precisely with the round bun through placement guides. Cheese coverage is optimized by placing the slice diagonally across the square patty. Lettuce folds are standardized to reduce overhang and dripping. Tomato slices are inspected visually for diameter and replaced if undersized. Onions are separated into ring layers to maintain consistent thickness. Pickles are spaced to prevent overlap or bunching. Sauce volumes are adjusted using pump restrictors. Each pump cycle delivers a metered dose that is verified weekly by weight checks. Dispense angles ensure center placement with minimal deviation. Top bun pressure is measured periodically to confirm compression does not exceed tolerance. Overcompression can cause lettuce or tomato slippage. Wrap tightness is checked by torsion testing with digital force gauges. Grill platen pressure is balanced to avoid sear marks that penetrate too deeply. Contact time is calibrated to match patty water content and surface heat conductivity. Belt tension is maintained through spring-loaded rollers at both ends of the grill. Drip pan contents are filtered and cooled before disposal. Grease flow is measured to calculate fat loss per batch. Each tray of patties is weighed at intervals to confirm moisture retention and yield. Conveyor speed is set to match maximum output per cook zone. Bun toast time is synchronized to meet grill exit timing. Topping replenishment occurs based on tray weight thresholds detected by load cells. Tomato and onion prep stations are cleaned and reset every few cycles to prevent buildup. Cheese trays are kept below 5 degrees Celsius using chilled gel plates. Lettuce bins are sloped for continuous access without compaction. Burger stacking alignment is controlled by operator training and guided bins. Variants like double burgers use the same assembly line with secondary patty placement after cheese. Burgers with spicy or grilled ingredients use segregated stations to prevent flavor transfer. All process parameters are displayed on line-side screens for real-time monitoring. Operators adjust pump pressure, toast speed, and tray positions based on on-screen instructions. Each station is time-stamped to maintain consistency across shifts. Ingredient freshness is managed by rotation schedules and bin timers. No topping remains in use beyond its designated holding time. Each component has a separate preparation and service life which governs when trays are replaced. The square patty ensures uniform cooking and reduces edge shrinkage. Griddle contact area is maximized by flat pressing. Consistent doneness is achieved across all patties through center-out thermal profiles. The full Wendy's burger is formed by layering precise ingredient units in defined order. Each addition is made at a fixed position along the conveyor. The sequence ensures balance in flavor, weight, and thermal distribution. Assembly line pacing is regulated by burger type, quantity, and order load. Stack height is limited by bun compression threshold. Burgers are finalized within a tight time window to maintain optimal serving temperature. Pizza Hut. Pizza production begins with the preparation of pizza dough using automated high-capacity mixers. Each batch starts with high-protein wheat flour dispensed from overhead silos through a pneumatic conveyor into a stainless steel mixing bowl. Water is metered precisely from a temperature-controlled supply line and delivered into the bowl through solenoid valves. Instant dry yeast is stored in sealed bins and dispensed by auger into the bowl after water. Salt and sugar are pre-weighed and released into the bowl from vibratory feeders mounted above the mixer. Vegetable oil is pumped from a storage tank through a heated line and added last to ensure uniform distribution. The spiral mixer begins in a slow speed mode for 1 minute to hydrate the dry ingredients. After hydration is complete, the mixer shifts to high speed to develop gluten structure. Mixing continues for 8 to 10 minutes until the dough reaches a defined elasticity and target temperature range. The dough is discharged into a trough and transferred to the divider using a hydraulic lift arm. The divider uses a piston system to cut dough into fixed weight portions based on pizza size specifications. Each dough piece is rounded into a ball shape by a rotary rounding mechanism and deposited onto a lightly floured tray. Rounded dough balls are conveyed into a temperature and humidity-controlled proofing cabinet. The proofing stage allows yeast fermentation to produce gas and relax the dough structure. Temperature is held around 38 degrees Celsius and humidity near 85% to maintain surface softness. After proofing for approximately 1 hour, the dough is moved to a pressing station. Each ball is loaded onto a heated platen, which presses the dough into a disc shape. Pressing is done with a hydraulic top plate that flattens the dough to a specified diameter and thickness. Heat from the platen sets the shape and prevents shrinkage during later handling. Pressed dough discs are transferred to perforated baking pans or screens using a vacuum lifter. A light mist of oil is applied to the pan surface to prevent sticking. The dough and pan then move along a conveyor to the topping line. Topping application begins with sauce deposition using a volumetric piston filler. The sauce is pumped from a heated holding tank and dispensed in a spiral pattern starting from the center of the dough. A rotating disc beneath the pizza ensures even coverage without manual spreading. Shredded mozzarella cheese is stored in chilled hoppers and fed to a depositor via a vibratory conveyor. Cheese is distributed through rotating paddles that drop a measured weight evenly across the surface. Cheese coverage is calibrated to stay inside the dough border. Additional toppings are added in a fixed sequence depending on pizza type. Pepperoni slices are dispensed from a rotary carousel that places overlapping slices in concentric rings. Cooked sausage crumbles are metered through a hopper with a gate-controlled release. Vegetable toppings such as mushrooms, green peppers, and onions are added from separate hoppers using calibrated volumetric scoops. Bacon pieces and ham strips are dispensed from compartments, lined with agitators to prevent bridging. Olives are dropped from a chute fitted with a shaker plate to ensure even distribution. Pineapple chunks are added last and drained before dispensing to avoid excess moisture. Each pizza proceeds to the oven loading belt, which is synchronized with baking time and oven speed. The pizzas enter a conveyor oven with a stone or mesh belt and a controlled baking chamber. Top and bottom heat are separately adjustable using electric elements or gas burners. Baking time is generally between 6 and 7 minutes, depending on pizza size and topping load. The oven is divided into thermal zones, which apply different temperatures to optimize crust and topping finish. Air circulation fans maintain uniform heat distribution within the chamber. Crust browning is controlled by bottom belt temperature and pan contact. Cheese melt is regulated by top zone intensity. Sauce bubbling and topping cooking are completed within the dwell time set by conveyor speed. Once baking is complete, the pizza exits the oven and is transferred onto a staging table with a heat-resistant surface. A metal lifter is used to remove the pizza from the baking pan if one was used. The pizza is then slid onto a cutting board positioned below a rocker blade cutter. The cutter is hinged to apply uniform downward pressure and is guided by slots in the board to maintain equal slice sizes. Standard cut configurations are 4, 6, or 8 slices depending on diameter. Each pizza is rotated to complete perpendicular cuts if required. Cut pizzas are transferred onto corrugated cardboard discs which serve as a support base. The pizza and disc are inserted into printed boxes by a sliding motion, which prevents topping displacement. Boxes are closed with a fold lock mechanism and stacked in batches on a heated shelf for holding. Specialty pizzas with cheese-stuffed crust use a different pressing process where cheese sticks are inserted into the dough edge before sealing. The dough is crimped mechanically to enclose the cheese along the perimeter. These variants are baked with slightly longer dwell times to ensure cheese softening. Thin crust pizzas skip the proofing stage and are sheeted directly after mixing. The sheeting line flattens dough using a 3-stage roller system that progressively reduces thickness. Sheeted dough is cut to shape using a rotating die and docked to prevent bubbling. It is transferred directly to the topping line without additional rise. Pan pizzas use thicker dough portions which are hand-pressed or machine-pressed into deep pans coated with oil. The oil creates a fried base texture during baking. These pans are baked longer at lower temperatures to prevent surface burning. Pizza Hut production lines are modular and can run multiple styles concurrently by using different lanes. Each lane is fed by a shared dough room and topping prep area. Toppings are staged in mobile chilled carts that are swapped based on menu rotation. Sauce preparation occurs in a separate area where tomato concentrate is blended with water and seasoning. The sauce is cooked in steam kettles and cooled rapidly before being pumped to holding tanks. Cheese is shredded in-house using rotary drum shredders or received pre-shredded in lined totes. Toppings are prepared using a combination of manual and automated methods. Whole vegetables are washed and sliced on rotating blade machines. Meats are pre-cooked and diced using high-speed dicers or crumblers. Toppings are loaded into color-coded bins and inserted into the topping line feed hoppers. Ingredient flow is monitored by load cells under each hopper, which signal refill triggers when weight drops below threshold. Each depositor is linked to a PLC that controls dispense rate, duration, and alignment. Pan and tray washing systems clean and sanitize bakeware after each use. Washed pans return to the pressing line in timed cycles. Conveyor belts are brushed and wiped at shift intervals to remove topping residue. All components of the pizza undergo mass balance verification to ensure recipe compliance. Each pizza's final weight is checked on a dynamic scale before boxing. Deviations trigger visual alerts and operator review. Conveyor speeds, depositor timing, oven temperatures, and cut configurations are all adjustable by touchscreen interfaces mounted on each station. Operators select pre-programmed recipes which load all parameters automatically. The dough formulation is calibrated to yield consistent rise, chew, and browning under standard conditions. Oil content determines tenderness, while yeast quantity controls gas production. Mixing temperature is adjusted based on flour temperature and ambient conditions to ensure batch uniformity. Cheese melt properties are influenced by moisture content and shred size. Sauce consistency affects spreadability and absorption into the dough. Topping order ensures base ingredient contact with heat for proper cooking. Every Pizza Hut pizza follows a defined flow from dough to boxed product. Each process stage adds a functional component that determines structure, flavor, or visual finish. Assembly is done in linear progression with limited manual input beyond topping reload and box stacking. Pizza format changes involve reconfiguring press molds, pan shapes, and depositor settings. Crust variants, such as garlic butter infused or herb seasoned, are handled by adding a post-bake brushing stage, where liquid toppings are sprayed onto the crust using a rotating nozzle arm. Pizzas with drizzle finishes or sauces applied after baking use a dedicated finishing table where squeeze bottle applicators or peristaltic pumps add final ingredients. These finishes are applied before boxing and allowed to set for several seconds. Temperature retention in boxes is enhanced by vent hole design, box material thickness, and stacking method. Pizza integrity during transport is preserved by maintaining alignment and minimizing topping shift through controlled insertion angles. Nescafe instant coffee is produced by extracting soluble coffee solids from roasted beans and then drying that extract into stable granules that dissolve fast in water. The process begins with green coffee beans that are cleaned to protect the downstream grinders and roasters. The beans pass over screens that remove stones and oversized debris. Air classifiers lift away light husk fragments and dust. Magnets capture metallic fragments before the beans enter storage bins. Roasting converts the raw beans into a brittle aromatic material that can be milled and extracted. Bins into a roaster at a controlled mass flow. Heat is applied in a programmed curve that drives moisture out first. As temperature rises, the beans expand and internal pressure opens micropores. Sugars and amino acids react and form brown polymers that deepen color. Volatile aroma compounds form and migrate toward the surface as the bean structure becomes porous. Roast control is managed by time and temperature and airflow. Airflow carries away smoke like volatiles and maintains uniform heat transfer. Roast endpoint is set to balance extraction yield and flavor profile. A lighter roast preserves brighter notes but can reduce solubility. A darker roast increases solubility but can add bitter roast solids. When roasting ends, the beans are cooled quickly to stop further reactions. Cooling air flows through a moving bed, so the beans drop below reaction temperature. Rapid cooling limits over roast drift and protects aroma. The cooled beans move into a degassing period where trapped gases begin to leave. Degassing reduces foaming and pressure issues in extraction. Grinding sets the surface area that controls extraction speed and selectivity. Beans are conveyed to roller mills or hammer mills depending on target particle shape. Roller mills crack and shear the beans into a controlled distribution. Hammer mills impact the beans and can create more fines. The grinder is tuned to create particles that allow fast water penetration, yet avoid excessive fines that clog filters. Particle size is classified after grinding. Screens and air classifiers separate fines from the main fraction. Oversized particles are returned to the grinder. The goal is a narrow band that supports stable extraction bed permeability. A stable bed keeps water flow even and prevents channeling. Extraction is the heart of instant coffee production. Ground coffee is loaded into extraction columns that operate as a countercurrent system. Hot water enters one end of the column train and spent grounds exit the other end. Fresh water meets the most exhausted grounds first. Water becomes progressively richer as it moves toward fresher grounds. Extraction temperature is set to dissolve desired solids while limiting harsh compounds. Higher temperature increases yield and dissolves more bitter fractions. Lower temperature preserves aroma but reduces yield. The system often uses staged temperatures across the column train. Early stages may run hotter for bulk solids. Later stages may run cooler to protect delicate notes. Pressure is used to keep water in liquid form at elevated temperatures. Pressurized extraction improves heat transfer and solubility control. Flow rate is regulated to maintain a target contact time. Contact time controls how far extraction proceeds before the liquid leaves the bed. Too short a contact time wastes soluble solids. Too long a contact time pulls more bitter fractions. The extract leaving the columns contains dissolved coffee solids and suspended, fine particles. Clarification removes those particles to improve final appearance and stability. The extract passes through screens that catch coarse fines. It then enters a centrifuge that separates suspended solids by density. Clarified extract flows forward, while sludge is removed for separate handling. Fine filtration can follow centrifugation. Depth filters capture remaining microfines that would create haze. Filter choice balances clarity and flavor. Too aggressive filtration can strip flavorful colloids. Too little filtration can leave sediment in the final granules. At this point, aroma management becomes important because extraction and clarification drive off volatile compounds. Many lines capture aromatics from roasting and grinding and early extraction vents. These aromatics are condensed into an aroma concentrate. The concentrate is stored cold to slow loss. It is added back later after drying or near the end of concentration. The clarified extract is still mostly water, so it must be concentrated. Evaporation removes water and raises solids content. Concentration is usually done under vacuum, so boiling occurs at lower temperatures. Lower boiling temperatures reduce thermal damage and preserve flavor. Falling film evaporators are common because they expose liquid as a thin film. Thin films evaporate fast and limit residence time. Solids concentration is controlled to a target viscosity suitable for drying. Too low a solids level wastes energy in drying. Too high a solids level becomes too viscous to atomize in a spray dryer. Sensors track density and refractive index as proxies for solids. Flow control keeps the evaporator steady so the concentrate remains consistent. Some product streams include a mild heat treatment during concentration. This can stabilize the concentrate by inactivating enzymes and reducing microbial load. The heating profile is kept brief to avoid cooked notes. Vacuum evaporation already reduces thermal stress, so the heat treatment can be minimal. After evaporation, the concentrate is cooled to a controlled temperature. Cooling protects aroma and sets viscosity for the selected drying method. The process then splits depending on whether the line makes spray-dried coffee or freeze-dried coffee. Spray drying converts concentrate into powder by atomizing it into hot air. The concentrate is pumped to an atomizer that forms fine droplets. A rotary wheel atomizer can create a narrow droplet size band. A pressure nozzle atomizer can create different droplet distributions. Droplet size controls final particle size and bulk density. Droplets enter a drying chamber with heated air. Water evaporates from the droplet surface first. A skin forms, and then moisture diffuses outward through the skin. The droplet shrinks and solidifies into a particle. Air temperature is controlled, so drying is rapid but not scorching. Outlet air temperature is a key indicator because it reflects remaining moisture. Powder leaving. The drying chamber is separated from air in cyclones. Cyclones spin the airstream and throw particles outward. Fine particles are captured efficiently and then discharged. Additional bag filters capture the finest dust. The recovered powder is cooled to prevent caking. Final moisture is set low enough for stability, but not so low that particles become overly fragile. Spray-dried powder can be too dusty and too fast dissolving. many lines agglomerate it to create larger porous granules. Agglomeration starts by re-wetting powder lightly with steam or water mist. Particles become tacky on the surface. They collide and stick into clusters. Warm air then dries the clusters and locks in the structure. The resulting granules have larger size and better sink behavior in water. Freeze drying follows a different path that preserves aroma and creates crisp granules. Concentrate is first chilled and then frozen into a solid slab or into pellets. Freezing speed controls ice crystal size. Larger ice crystals create larger pores after sublimation. Smaller ice crystals create finer pores and can slow dissolution. Frozen coffee enters a vacuum freeze dryer. Under vacuum, the ice sublimates, which means it goes from solid to vapor without melting. Heat is added gently through shelves or radiant plates. Sublimation leaves behind a porous matrix of coffee solids. The structure is brittle and breaks into irregular granules. After freeze drying, the dried slab is milled or fractured into target granule size. Screening separates fines and oversize. Oversize is reduced further. Fines can be recycled into agglomeration or blended depending on product targets. The granules are then conditioned to equalize moisture and temperature. Aroma restoration is typically applied after drying because high heat and vacuum remove volatiles. Aroma concentrate is dosed onto the dry granules in a closed blender. The granules tumble while a fine spray coats their surfaces. The coating is absorbed into pores and binds by capillary action. The system controls spray rate to avoid wet spots that cause clumping. Some lines also perform a light surface polishing. This step reduces dust and improves flow in packaging. Polishing can be done by gentle tumbling that knocks off loose fines. It can also include a tiny amount of food-grade anti-caking agent. The application is kept minimal, so it does not change flavor release. Quality control at this stage focuses on moisture and bulk density and dissolution time. Moisture affects shelf stability and clumping. Bulk density affects dosing in jars and sticks. Dissolution time affects consumer experience in hot and cold water. Particle size distribution is measured because it controls flow and dust. Blending is used to keep flavor consistent across production lots. Granules from different runs can be blended to average variations. Blending equipment uses gentle paddles to avoid crushing. The blender also equalizes aroma addition across the batch. Sampling confirms uniformity by checking aroma intensity and color and soluble solids. Nesquik chocolate drink mix is manufactured by turning cocoa and sweetener into a free-flowing instant powder that wets fast and disperses without floating clumps. Production starts with bulk ingredient receiving and conditioning. Sugar arrives as granulated crystals and moves into silos with controlled humidity. Cocoa powder arrives in lined totes and is kept in a dry room to prevent caking. Milk-derived powders can be included for creaminess, and they are stored cold enough to stay free-flowing. Minor ingredients like salt and flavors arrive in sealed drums to protect aroma strength. Vitamin and mineral premixes arrive as low-dose powders that require tight segregation for accurate dosing. The line begins with particle preparation because every downstream step depends on predictable flow. Sugar is screened to remove oversized crystals that can separate during blending. Sugar fines are managed because excessive fines increase dust and can make the mix pack too tightly. Cocoa is sifted through vibratory screens to break soft agglomerates. Any fibrous lumps are removed to prevent specks in the final product. Milk powders are sieved with larger mesh to protect fragile particles from unnecessary grinding. Cocoa powder requires special handling because it is hydrophobic and tends to float. The powder surface contains natural fats that repel water. This property is the main reason Nesquik needs instantizing steps. The process therefore focuses on building granules that pull water in quickly. It also focuses on adding emulsifiers that lower surface tension and improve wetting. Weighing and batching starts once each ingredient is within specification. Large-scale ingredients are metered by loss in weight feeders. The feeders deliver sugar and cocoa at controlled rates into a pre-blend hopper. Medium-scale ingredients like milk powder and maltodextrin are metered through secondary feeders. Very low-dose ingredients like vitamins are added through micro feeders with screw dosing. Each feeder is calibrated so the recipe ratio stays stable across long runs. Pre-blending is used to prevent micro-ingredient streaks. Sugar becomes the carrier phase because it has high mass and flows well. Micro-ingredients are first blended with a small portion of sugar in a ribbon blender. This creates a dilute premix with uniform distribution. The premix then rejoins the main sugar stream and reduces the chance of hot spots. The main blending step combines sugar and cocoa into a uniform base. A high-capacity ribbon blender or plowshare mixer is common here. The mixer creates strong folding action that lifts powder and then lets it fall through a shear zone. Cocoa is dispersed into sugar so the color becomes even. Mixing time is controlled because overmixing can create electrostatic charging and dust. Undermixing leaves cocoa streaks that show up as dark clusters in scoops. Flavor addition happens during the main blend or just after it. Vanilla flavor is often added as a liquid or as a dry encapsulated powder. Liquid flavor is sprayed through a fine nozzle into the moving powder bed. The spray rate is low to avoid creating wet clumps. The mixer speed is increased briefly to distribute the liquid film. Dry flavor powders are easier to distribute, but they still need good agitation to avoid pockets. Salt is added in small quantity, and it must be dispersed evenly. Salt crystals can segregate if their size differs from sugar. Many lines use fine salt or salt dissolved into a small liquid addition. When salt is added as a dry powder, it is often included in the premix step. This reduces segregation later in transport. If the formula includes vitamins, the process emphasizes gentle but thorough distribution. Vitamin premixes can be sensitive to heat and moisture. They are added after any warm steps to reduce loss. They are also protected from intense shear that could break protective coatings. The blender uses a defined sequence so the vitamins are introduced after the bulk powders have already become uniform. At this stage, the powder is blended, but it still has poor instant properties. Cocoa will still float and form islands on water. The next stage is instantizing, which converts fine powders into porous granules that sink and disperse. There are several ways to instantize. A common route is agglomeration with a wetting step followed by drying and cooling. Agglomeration starts by feeding the blended powder into a controlled chamber. The powder forms a moving curtain or a fluidized bed. A binder is then applied as a fine mist. The binder can be water or sugar syrup depending on the target density. The binder lightly wets particle surfaces and makes them tacky. Tacky particles collide and stick into clusters. These clusters grow into granules as more powder adheres. Granule growth must be controlled tightly. If binder is too high, the granules become large and hard. If binder is too low, the granules remain dusty and fragile. Airflow and chamber turbulence control collision rate. Residence time controls final size. The process aims for granules that feel light and porous. Porosity is important because it creates capillary channels that pull in liquid. A key improvement step is lecithination. Lecithin is an emulsifier that improves wetting and reduces surface tension. Lecithin can be applied as a liquid spray onto moving powder. It can also be applied as a solution in a volatile carrier. The spray coats granule surfaces and migrates into pores. This makes cocoa less hydrophobic in the cup. The dosage is low, but the impact on dispersibility is large. When lecithin is applied, the process must avoid creating shiny wet spots. Spray droplets must be small and evenly distributed. The bed must be moving vigorously so the film spreads. Temperature is controlled, so lecithin stays fluid during application. After application, the granules are dried slightly to lock the surface condition. Drying follows agglomeration because binder adds moisture. Drying is done with warm air moving through the granule bed. Air temperature is chosen to remove water without changing flavor. Too much heat can drive cocoa volatiles off and dull aroma. Too little heat leaves moisture that causes caking in the jar. The dryer controls inlet temperature and outlet humidity to reach a target moisture. Drying also stabilizes structure. As moisture leaves, the binder creates bridges between particles. These bridges set granule strength. Strong enough bridges prevent breakdown into dust. Weak bridges create fines during conveying and filling. The process tunes drying time to meet a target crush strength. That crush strength must still allow fast dissolution in the cup. After drying, the product is cooled. Cooling prevents condensation in packaging and reduces clumping risk. Cooling air is dehumidified, so it does not add moisture. The granules exit at a temperature close to the packaging room temperature. This prevents moisture migration when the product enters sealed packs. Screening and sizing occur after cooling. Vibratory screens remove oversized agglomerates that would dissolve slowly. Screens also remove fines that create dust and poor wetting. Oversize can be milled lightly and returned to agglomeration feed. Fines can be recycled as seed material for new agglomeration. Recycling is controlled, so the powder does not build up too much fine content. Some lines add a final dry blend step after agglomeration. This can be used to add heat-sensitive vitamins. It can also be used to add a small amount of anti-caking agent. Anti-caking agents are used at very low levels to keep flow stable. They are distributed with gentle mixing to avoid breaking granules. The blend time is short to protect structure. Density control is a major target for drink mixes. Bulk density affects spooning and packaging, volume and consumer dosing. Agglomeration tends to lower density because it creates porous granules. The process tunes binder and airflow to hit a defined density band. Too low, a density makes scoops inconsistent. Too high a density can reduce instant performance. Flowability control is equally important. Granules must flow through hoppers without bridging. They must also settle consistently in jars. Flow is improved by uniform granule size and low moisture and smooth surfaces. Excess fines degrade flow because they increase cohesion. The screening stage, therefore, has a strong influence on packaging efficiency. Color uniformity is checked because cocoa distribution must remain stable. Color drift can indicate segregation or inadequate mixing. If the product includes added micronutrients, the line checks distribution by sampling and chemical analysis. Uniform distribution is achieved mainly by the premix approach and by stable blender loading. The product then moves to packaging feed systems. Gentle conveyors are used to protect granules from breakage. Bucket elevators can be used with low drop heights. Pneumatic conveying is possible, but it can create fines if velocities are high. When pneumatic systems are used, the line uses low velocity dense phase conveying. Bends are designed with large radii to reduce impact. Packaging for Nesquik can be in jars or canisters or sachets. For canisters, the product is filled by volumetric auger fillers. The auger rotates and dispenses a controlled volume of granules. The fill weight depends on bulk density, so density must remain stable. Check weighers confirm the filled mass and reject outliers. The canister is then capped with controlled torque to maintain a moisture barrier. Starbucks coffee starts as green beans that are transformed by controlled roasting, rapid cooling, precision grinding, and oxygen-managed packaging, so flavor remains stable until brewing. Green beans arrive as a hard, dense seed with moisture locked. Inside cell structure. The first job is cleaning because even small hard contaminants can damage rollers and grinders. The beans pass through screens that remove stones and broken fragments. Air separation lifts away chaff and dust. Magnets capture metallic particles before the beans enter storage bins. Storage is designed to keep bean moisture and temperature steady. Beans are blended from different lots to hit a target profile before roasting begins. This blending step is a physical averaging process. It reduces variability in density and moisture that would otherwise shift roast development. Roasting begins with accurate feed control. Beans enter a roaster at a fixed mass rate, so heat transfer remains consistent. Hot air and heated metal surfaces raise bean temperature in a staged curve. Early roasting drives off free moisture. Steam leaves the bean and pressure builds inside pores. The bean structure expands and becomes more porous as internal water turns to vapor. As temperature rises further, chemical reactions generate color and aroma precursors. Sugars and amino acids react and produce brown polymers that deepen color. Oils migrate toward the surface as the bean matrix opens. Gases form inside the bean and create internal pressure that changes cracking behavior. The roast curve is adjusted so reactions progress without scorching the exterior. Airflow is a main control lever during roasting. Higher airflow increases convective heat transfer and carries away smoke like volatiles. Lower airflow increases contact time of vapors and can intensify roast notes. Exhaust control keeps the roast environment stable, so each batch follows the same thermal history. The roast endpoint is defined by bean temperature and time at development conditions. A shorter development phase preserves brighter notes but can reduce solubility. A longer development phase increases solubility and roast character. The endpoint also influences how easily the bean grinds. A darker roast fractures more easily and produces more fines at the same grinder setting. When the endpoint is reached, the beans must be cooled fast. Cooling stops reactions that would continue from residual heat. Beans drop into a cooling tray or a cooling conveyor. High airflow pulls heat out rapidly and reduces carryover roasting. The target is a uniform final bean temperature, so later packaging does not trap heat and create condensation. After cooling the beans, enter a degassing phase. Roasted beans contain carbon dioxide trapped in pores. Degassing releases gas gradually and changes how the coffee behaves in packaging. If beans are packed too soon, pressure can build inside bags. If beans degar too long, the most volatile aromas can decline. The process chooses a defined rest window that balances gas release and aroma retention. Quality sorting can occur after cooling. Optical sorting can remove scorched beans and pale beans. Density sorting can remove light defects that roast differently. This step tightens consistency in the final bag because even a small number of off beans can alter brewed cup perception. From this point, production splits into whole bean and ground coffee paths. Whole bean coffee moves toward packaging with minimal mechanical stress. Ground coffee requires additional size control because particle distribution defines extraction speed in the brew. Grinding begins with grinder selection based on product format. Roller mills produce a more uniform distribution with fewer extreme fines. Burr-style industrial grinders create a controlled cut with predictable heat generation. Grinder settings define the median particle size and the tail of fines. The fines fraction matters because it drives bitterness and slows flow in filter brewing. Temperature control during grinding protects aroma and reduces clumping. Grinding generates heat from friction and impact. If coffee warms, too much volatile compounds flash off. Warm grounds also pack and bridge more easily in hoppers. The line manages temperature by controlling throughput and by using cooled air or staged grinding. After grinding, the coffee is classified. Vibratory screens or air classifiers remove oversized fragments and reduce the fraction of dust. Oversized fragments can be returned to the grinder. Excess dust can be blended into other streams in controlled amounts or removed depending on target. Classification improves brew repeatability and improves fill accuracy in packaging. Aroma management becomes more critical once coffee is ground. Grinding exposes fresh surface area and accelerates oxidation. The process, therefore, reduces oxygen exposure time between grinding and sealing. Conveying is often enclosed and may use inert gas in certain steps to reduce oxygen pickup. The goal is to keep oxygen away from oils on particle surfaces. Packaging is built around barrier films and controlled headspace. Bags or canisters are formed and then filled by weight. Auger, fillers, and vibratory feeders deliver grounds in measured pulses. Fill chutes are designed to reduce dust and keep seal areas clean. Weight checks confirm each unit meets target. For whole bean bags, the filler drops beans gently to avoid fracturing. Fractured beans create fines at the bottom of the bag. They also create more surface area for oxidation. Drop heights are minimized and chutes use smooth curves rather than sharp bends. Many coffee bags use a one-way degassing valve. The valve allows carbon dioxide to escape without letting oxygen in. This supports earlier packaging because gas can leave after sealing. It also reduces bag swelling during distribution. Valve application is done as part of bag manufacturing or as an inline step before filling. Sealing closes the package and locks in the controlled atmosphere. Heat seals must be strong and continuous. Seal jaws apply temperature and pressure for a defined dwell time. If dust sits in the seal zone, the seal can leak. The line, therefore, controls dust by extraction and by nozzle cutoff design. Once sealed, the packages move through coding and inspection. Vision systems can confirm seals and valve presence. Check weighers confirm net weight. Metal detection can be used as a final protection step. Units are then packed into cases with orientation that protects valves and reduces crushing. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled, so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming, so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming, so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or Sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing, the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. Proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources such as vegetable oil or butter are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix.